Hello, everyone, and welcome to this latest webinar from Omdia, brought to you by Informatech. My name is Alan Tatara, Senior Event Manager for the Omdia webinar team, and I want to thank everyone for joining us. Today, our topic is Pluggable Coherent Modems. The future is here. Our panel will explore how network operators are using interoperable pluggable modems for new applications, all while decreasing their capex and operating costs. Our webinar is co-presented by Omdia and our partners Acacia Communications, Siennas, and Nokia. So before we get started, let me just highlight and walk you through some of the features on our webinar so you can completely customize the console that is in front of you by opening, closing, moving, or resizing any of the windows and arrange the console any way you like. Now, I want to make sure you check out all of those application widgets at the bottom of your screen, especially the resource list widget, because this is where you're going to find additional material about our topic, including the downloadable slides from today's session, as well as other valuable information, including a special report authored by analyst Timothy Monks. If you want to follow our conversation on Twitter, just click on that widget and make sure you use the hashtag #CoherentPluggables. We will have a live Q&A session right after our presentation, so please remember to submit your questions or comments at any time by using that Q&A widget that is on the left side of your screen. Now, this webinar is being recorded, and note that the on-demand version will be sent out to you within about 24 hours. And if you experience any technical issues, just click on that question mark widget and you will get the information that you need. All right, so let me take this opportunity now to introduce to you our panel. First leading our discussion is Timothy Monks. Tim is a senior principal analyst in the high-speed optics and optical network technologies segment at Omdia. Joining Tim is Tom Williams. Tom is the vice president of marketing at Acacia Communications. We are also joined by Patricia Bauer. Patricia is senior manager of portfolio marketing at Siennas. And rounding out our panel, we have Kyle Hollish. Kyle is the Director of Optical Portfolio Marketing at Nokia. So welcome to our speakers. It is an honor to have you with us today. So now I'm going to turn things over to Tim so we can get started. Tim?
Thank you, Alan, and welcome everyone to our webinar on Pluggable Coherent Modems. With Acacia, Siennas, and Nokia, we have some of the leading innovators in coherent optics. So it's a great panel, and we've got a lot of stuff to get through today. So why don't we get started? So this is kind of the outline of the webinar. First, I'll go through some of the market trends and kind of set up the webinar. And then our panelists will go through and talk about the problems and challenges facing the industry, new options and solutions to face those challenges, deployment applications where these new solutions might be used. And then we'll have each of the sponsors go through their approaches. And then finally, I will give some concluding remarks and we'll move into the Q&A session. So, okay, let's get started with the market trends. This first slide, many have maybe seen this or something like it before, but I wanted to do a edge DCI comparison, looking at traditional embedded solutions and how that compares to the 400ZR. So if you look at the traditional DCI, and this is done with DWDM equipment, you're going from top of rack to an edge router, and basically you're going through client transceivers or datacom transceivers between that and the optical transport equipment. So if this is at 400 gig, the client or datacom, you've got 400 gig that is up here going through a duplex fiber to another 400 gig here, and then it goes into the optical transport system over a line system to another transport system and does the reverse back to the edge router. So you've got OEO conversions, a lot of those, and then over the DWDM optical transport. Now, one thing to point out, though, this DWDM optical transport, this can be used for connecting up, data centers, whether they're next door, or they're across the country, or even across the ocean. So, you can do those connections over metro, regional, long haul, and even subsea networks. Now, looking at connections with 400ZR, it's quite a bit simpler. You're actually plugging in these high density form factors right into the edge routers and going over an open line system. And this may be, data centers that are 10, 40, 80 kilometers apart with a ZR. So quite a bit simpler. And if you look at the bill of material comparison in these, you've got the datacom transceivers, you've got the extra duplex fibers between those transceivers out to the optical transport gear. And then with the ZR, you've just got the two pluggables, and the open line system don't need the extra fiber inside the data center. So quite a bit simpler, and that's why we think this will be a very important transformation of these type of applications, these kind of point-to-point applications. But there's still a lot of networks that need more than point-to-point applications. So anyway, that's kind of a comparison there. Next, I wanted to go through kind of the 400 gig update and forecast. And so there's been a lot of thoughts out here that these pluggables are going to replace everything. That's just not the case, right? I mean, these embedded or performance optimized solutions are still growing. They're not going to be growing as fast relative to pluggable solutions, but they're still growing, and they still will be in our forecasts. We expect them to have the lion's share of the market, the 400 gig plus. So this is 400 gig, it's 600 gig, 800 gig, and then whatever's next, we expect there will be at least one generation of products in there in this forecast time. And then there's another pluggable. This is the ZR Plus, which means a lot of things to a lot of different people. But it's a pluggable for more metro regional applications where there's higher performance, is going through more ROADMs. And what we're kind of expecting is that the pluggables for these point-to-point type applications will dominate those, and the embedded for long haul and subsea will dominate those. And then the competition's really going to be in this middle, in the metro regional area, where it's going to be a competition between ZR Plus, which are probably going to be in CFP2 packages, although there may be some in the higher density packages as well, with the embedded, the performance optimized solutions. And that's where we're expecting this. I think in this forecast, I'm pretty conservative on the ZR Plus. Because it's still somewhat ill-defined, and also it's in the trial phases now, so we don't understand all the applications that might end up using that. But that's where we expect the real battle is going to be is between the embedded solutions and the ZR Plus type solutions going forward. Okay, so looking at deployed bandwidth, so this is something we've been modeling for quite a while. We get inputs from several of the key coherent vendors, and since we've had these multi-haul or multi-rate modems, it's been harder and harder to look at deployed bandwidth. But with the input from several of the vendors on, say, how a 400 gig operates, where 20% are at 400 gig, 30% are at 300 gig, 40% are at 200 gig, and the remainder at 100 gig. Then we take that and model that out into the whole thing and look at how bandwidth's being deployed. And it's something we've been tracking, and we're growing bandwidth at about 30% on a compounding annual basis. So that's doubling about every 2.5 to 3 years. And I guess right now, if you look at it in 2021, Even in 2020, 200 gig really took over more, is deploying more bandwidth than fixed 100 gig. We are expecting 100 gig to start growing again when some of these new pluggables come online and there's applications for them. But, 100 gig's been slowing down here over the last couple years, but we expect that those type of products will bring some growth. So that's it for the market introduction. I'm going to turn it over now to Kyle to go through the problems and challenges facing the industry.
All right, thanks, Tim. Glad to be here. So I think Tim's chart there was really good, showing deployed bandwidth growing at 30% a year, which of course mirrors bandwidth demand, which is growing at 30% a year, and that's really fast. So our most important task as optical systems vendors and component vendors over the past number of years has been reducing the cost per bit, because that's the only way that network operators can stay afloat, by continually reducing that cost per bit. And over the last 10 years, let's call it the 100 gig era, coherent DSPs, coherent technology has really been able to achieve this largely by increasing spectral efficiency. And so spectral efficiency increases our C-band capacity, significantly, roughly at that 30% per year. And as we've been doing that, we've kind of been riding the wave, riding the curve of Moore's law, if you will. And so the power per gig and the size per gig of these coherent interfaces has been continually decreasing as well. And so now, as we kind of enter this 400 gig era, we know that we're approaching the Shannon limit in terms of spectral efficiency. And so there's really not going to be a lot of gains, a lot of cost per bit reduction that we can wring out of networks purely by spectral efficiency, and certainly not economically. But if we look at this curve where we have Moore's law, now maybe it's slowing down a little bit, but it certainly chugs on in terms of the ability to reduce cost, reduce size, reduce space that is provided by silicon technology. And so as we enter this 400 gig era, we're going to see a lot of investment shift to continuing to ride that Moore's law wave via tighter integration, silicon photonics, innovations in DSPs, and that's where continued cost savings is largely going to come from. So I'll turn it over to Tom for some more details there. Sorry, I just over-advanced on you. There you go.
Thanks, Kyle. Yeah, I think we both advanced at the same time.
Let me finish this one, and then I'll
let you take it.
There you go. It's yours. It's yours.
Okay, great. Thanks, Kyle, and totally agree with everything Kyle just said. As we have increased capacity, if you look back over the last 10 years or so, we've had rapid increase in data rate, and as we went from 10 gig to 40 gig to 100 gig to 200 gig, we were still operating within a 50 gig channel. And so the increase in capacity not only made more efficient optics because you're pushing more bits over the same number of optics, but also increased your capacity per fiber. So the efficiency of that, was in multiple dimensions. We were making more efficient networks. As we approach Shannon limit now, we have networks that are very, very tightly coupled between the transmission spectrum and the passband of the filters, and so we're getting very close to the maximum amount of transmission, the Shannon limit, and so it's becoming more difficult to take those big steps in performance. It's small improvements in performance are costing significant amounts of power, and there are places in the network where that is worth it, and that will continue to be where you want to maximize that last little bit of the fiber capacity in long-haul submarine networks, and those will continue to have very highly performance optimized solutions. But there's a lot of parts of the network where we need to find other ways to make more efficient networks. And so when we look at this problem, as we look at the transition, I think what Kyle said is certainly true. We'll look towards silicon to be the driving force behind that next wave of innovation. Higher levels of optical integration, we believe that'll be in silicon, and also scalability of designs so that we can ramp and address high volume applications, And then also aligning all of our technology and all of our solutions with these high volume applications. So I think as we look forward toward some of these pluggable and standardized solutions, we should do so in a mindset of how do we drive the volume to these applications, and then how do we leverage the volume in those applications so that we can efficiently develop all the other solutions that we need based on common technology. And with that, I am going to turn it over to Patricia.
Okay, thanks, Tom. So as a natural evolution of coherent technology, where we move forward along those curves of increasing capacity or reducing size, as Tom and Kyle have outlined, I think it's helpful to look at the drivers from a network operator perspective and how this new paradigm, how these pluggable coherence modules are going to be addressing the needs of new architectures. And so there's three network segments outlined here in this chart. And in the first row, we have single span DCI. And one of the challenges here is a requirement for massive bandwidth interconnect, particularly for those hyperscale data center operators looking to extend their switch fabric across multiple data centers. So this significant capacity growth needs to be supported, all while mitigating for space and power. And in this case, 400 gig pluggable coherent technology, specifically 400ZR, will support this massive parallel connectivity and also support reduced footprint through IP-optical integration, as well as meeting the volumes and economics needed through a multi-vendor ecosystem. And in the second case, we have metro regional networks, and here providers are looking to reduce costs for lower capacity transport, where, for example, the installed base of fixed grid ROADM networks might not allow for the use of the latest and greatest higher baud coherent technology. So here, coherent pluggables can offer that migration through higher capacity on a per rack unit basis. Fixed grid systems can evolve to lower power, higher density 100 gig, 200 gig to transport links. And there's a path to IP-optical convergence enabled for new network buildouts. And then in access applications on the bottom, where more bandwidth is needed for edge connections, there's a network modernization underway to upgrade from legacy 10 gig connectivity, while also covering thousands of sites and contending with things like exterior deployments. So here, coherent pluggables may eventually replace gray optics, offering really a step function improvement in capacity, be supported in converged IP-optical platforms as well. And coherent technology in this case will support really longer distances than the legacy technology, as well as offering multi-vendor economics. So pluggables will offer higher capacity at reduced power and footprint, and an opportunity for new architectures based on converged IP-optical platforms with no penalty in switching density. And we expect the use of coherent pluggables to be pervasive in the network where it makes sense. But for sure, there are operational and networking issues to be taken into consideration, given the constraints imposed by the compact plug form factors with respect to the features and functions and performance they can support. So the first of these is whether it's a greenfield or a brownfield deployment. In the case of a greenfield deployment, both or either of the photonic line system and host platform can be optimized for the choice of pluggable coherent modem. But if it's a brownfield deployment, consideration of the existing channel plan will determine what pluggable optics will fit based on what symbol rate is supported, how it fits in the filters, and this will influence the wavelength capacity that can be achieved. Another question is whether or not the deployment is for a fixed or flex grid ROADM infrastructure. This requires a compatible symbol rate to the fixed channel filters. And flex grid applications require sufficient transmit OSNR, for example, to mitigate out-of-band noise. In line-side engineering, there are many elements that can impact the choice and deployment realities for pluggable optics and the resulting impact on the network. So removal of functions, modem functions to fit, for example, in a very small QSFP-DD package, amplification, filtering, network functions like encryption, OTN support, means they need to be implemented elsewhere in the system to avoid performance penalties, or just simply the function has to be captured elsewhere. We also know there's a fairly large impact on performance depending on the type of channel mux demux used, and there needs to be good optimization between the plug and the line system. Planning for restoration paths is another consideration. The working path can be clearly specified, but the restoration path could be longer, there could be more than one, and this influences the choice of technology. And design tools are key elements that allow operators to plan for and manage multiple generations of coherent technology in the network, and are an important factor in planning for the use of new architecture elements like coherent plugs. And finally, future-proofing. Choices for optical technology and architecture today influences what is possible in the future as today's greenfield becomes tomorrow's brownfield. So now we're moving into section 3, which is new options and solutions. And here I'll hand it over to Kyle to kick this section off.
All right, thanks, Patricia. So I'm going to take a little bit of a step back. I think we've done a really good job, Tom and Patricia, of kind of covering some of the operator challenges here. But let's look at where we are in terms of this big 400 gig inflection point. So we know that 400 gig E is going to drive that next wave of router investment. With 25 terabit switch fabrics, you absolutely need 400 gig just to get the data off of the line card. That's going to drive investment there. Going along with that, we need 400 gig wavelengths to transport those 400 gig ports. They're clearly going to become the new network currency. They're already deployed in networks, but there's going to be so many ways to deploy them at different cost and performance points, and that's going to drive it really as that common currency. So, of course, what this webinar is all about is DCOs. They're going to enable IP-optical integration potentially, and they're really just going to dramatically impact that that cost curve that I started the webinar with. And then lastly, we complement DCOs with the latest generation, currently 90 gigabaud, call it 400 gig any distance technology that really goes hand in hand with DCOs to allow 400 gig really everywhere in the application space. So speaking of 400 gig everywhere, we have a broad range of interfaces, and Tim started to mention these when he had his growth curves up there, but I put pretty pictures on. And so we have 400 ZR there on the left, and that's really getting all the attention in terms of being OIF standardized, meeting this web scale data center interconnect application, likely going to be primarily in QSFP-DD. But as we go to the right, we have increasing performance. And so ZR Plus could be in a small client form factor or potentially a larger form factor, going to meet more of those metro aggregation type applications. When we get into the CFP2 form factor, call it potentially multi-haul is a term that we use for it. Now we can address metro core and regional networks, because in that larger power envelope and space envelope, we can fit higher power transmitters, more features, more functionality in order to get the kind of optical performance that we're accustomed to in optical transport systems. And then lastly, for high performance long haul subsea applications, we have that what Tim referred to as embedded technology, 400 gig any distance technology. And then in terms of where these are going in terms of hardware, we're generally going to see router-hosted coherent optics on the left, where the form factor is suitable to routers. And then over on the right, where it's embedded, that's going to be within a WDM system-based coherent optic. But in the middle, there's some gray area, certainly around the CFP2 form factor, and even potentially in the ZR Plus form factor, the QSFP-DD, where we might see it span both router-hosted applications as well as WDM system-based applications. And so, as Tim mentioned, kind of the battleground, both technologically and in terms of the market, is in that middle. I'll turn it over to Tom next to go into some more details. I'll let you advance it, Tom.
Great, thanks, Kyle. And I'm clearly also a fan of the pretty pictures of modules. So I'm going to take kind of what Kyle talked about in the different solutions and talk a little bit about standardization that has taken place in this generation of pluggable modules. And it's important to remember pluggable coherent modules isn't a new thing. It's been around for quite a few years, going back to 2014, 2015, when we first introduced the pluggable CFP. And it's widely deployed, particularly in China. What is really new about this generation is the level of standardization of really high performance pluggable modules that really push us very close to what is available in that kind of best in class performance solution. So not quite to the edge, but to a nice level of performance that can meet a lot of applications. And so all of this standardization started in OIF with the 400ZR. And that was back in late 2016. that got kicked off and was really targeting a specific application, 400 gig clients, 400 gig on the line, DCI edge applications, and very simple use case. But then other applications and other types of network operators started looking at that and saying, how can I leverage that? And Open ROADM, in a more carrier ROADM-based environment, looked at that and said, I need a solution that is very similar but higher performance and more functionality. So that introduce more functionality on the client side, more data rates. So you're not limited to just 400 gig. If you need to go a longer reach, you can go 100, 200, 300, or 400. And additional functionality which didn't have to be constrained by the very small QSFP-DD, OSFP footprints and sort of had in mind a CFP2 type footprint. So more like the model where pluggable coherent has traditionally been deployed. And then OpenZR Plus is sort of a hybrid of the two, where it took some of the high performance and certain functionality to expand the use case, but still with the smaller form factors in mind. So still targeting router applications, but now supporting multiple rates on the client, multiple rates on the line, using the higher performance FEC, and sort of provided a balance between the two so that it could address a range of applications in between. So what we have here is leveraging some common technology to address a range of different network applications. And in fact, also the same generation as applications in the access network started to look toward coherent. Cable Labs looked at this investment going on and not necessarily at 400 gig, but they defined standards at 100 gig and 200 gig that also leverage some of this common technology for access aggregation applications that are looking to take multiple 10 or 25 gig inputs, aggregate them into a 100 gig or 200 gig stream, and leverage coherent technology so that they can achieve longer reaches, have a simpler operational model, and take advantage of all of the benefits for coherent. So, the common theme here is a whole generation of components and standards that have been defined that allow us to make a big investment and then support a range of different applications. And with that, I'll turn it over to Patricia. I'll let you advance it.
Okay, thanks, Tom. So multi-vendor interoperability is certainly one of the goals for specific types of coherent pluggable deployments. And this is supported by a range of standards and MSAs, as some of what Tom outlined. PMs, or performance monitoring metrics, are accessed via the DSP internal to the coherent pluggable modem. They're one of the key tools available to network operators to validate the health of the optical link serviced by the plug. So there's a phase beyond standards or MSA-defined interoperability, and that's operational interoperability, where the industry would aim to get closer to plug and play over time. So PM accuracy and consistency is critical in a multi-vendor operational deployment. And in this chart, we show an example with 400ZR. So in the OIF implementation agreement, or IA, there are certain basic interop elements covered from the perspective of both the core DSP and the line. So these include items for the DSP, such as the host interface supporting the 400 gigabit Ethernet, 400G base R client signal, the type of forward error correction, the symbol rate baud, the constellation, the type of framing, some link status, link degrade alarms based on FEC, some test vector validation, so that's the DSP data path vendor-to-vendor validation. And it also includes some items for basic line interop, such as the definition of the 80-kilometer blacklink optical channel and the associated channel spacing. Also, transmit and receive optical specifications, and some limited interop test methodologies, such as loopback tests and EVM, error vector magnitude measurements. So beyond that, if we move down the chart, there are a set of additional specifications for operational interop. And these include elements like mechanical and thermal measurements, case, laser, DSP temperature, voltage ratings, transmit and receive optical power, pre and post spec bit error rate, modulator bias, a respective balancing of the X and Y polarizations, and a host of optical channel characteristics, chromatic dispersion, polarization mode dispersion, optical signal to noise ratio, so on. So these PMs, to a certain extent, are listed in the host management interface specification, or coherent common management interface specification, the CCMIS, for the line side. But some further work is needed to cover accuracy, and this would be guided to a large extent by link engineering requirements. And one specific example is OSNR, which is a PM that is subject to some variability, has some sensitivity calibration errors. So there are alternatives such as ESNR, for example, are being considered for potential updates to the implementation agreement. And then in addition to line performance and interop, there are also the mechanical and physical constraints to consider. We've entered the era of coherent in a gray optics form factor. So for example, DWDM applications requiring high density faceplate configurations, such as those serviced with QSFP-DD form factors, operational viability depends on the host cooling environment, which is ultimately impacted to a large extent by the power dissipation of the coherent pluggables on the front panels. So this example highlights 400ZR again, and the density in a DCI hub switch that equates to a couple hundred QSFP-DDs. So in this host environment, the power dissipation of the individual plug is critical as the effect is multiplied across the switch and then across the data center. So additional power per plug drives higher cooling fan power. That's an exponential relationship. And that in turn leads to higher cooling capacity requirement for the switch chassis. There's also the additive effect that more heat passes over the core switch, requiring still more fan power. So taken all together, this translates to higher fan power consumption, and this has an overall additive impact on OPEX for the data center. So the goal to minimize power dissipation of the plug itself, which was captured as an intention in the 400ZR IA, has real-world cost implications for the end user when it comes to operational deployments. So now I think we're moving to section 4, and I'll hand it over to Tim to kick that off.
Thanks, Patricia. Yeah, I just wanted to come in and remind everybody after the webinar, we will be doing audience Q&A. So if you do have questions, please submit those in the Q&A box, and we'll get to as many of those as possible. What we don't get to, we will follow up with email. Okay, I'm going to turn it back over to Patricia for our sponsors approach. Here we go, Patricia.
Okay, so I think we're looking at deployment applications, and so we're kicking off here with just a quick review of coherent pluggable applications in some different segments, and this is just showing them really in relation to traffic capacity on the y-axis and traffic distance or reach on the x-axis, and in the 400 gig capacity range, we have the key example, which is 400ZR as a short reach application. This is defined by the OIF, also covered in ongoing IEEE efforts for single-span DCI. We expect 400ZR pluggables to support a couple of different deployment scenarios. One is on transport platforms where you'd be supporting a mixed switch router environment, and that would also support demarcation. And the other key application is of course, direct on switch platforms, and that would be in a homogeneous 400 gigabit router environment. With a mix of 100 gig, 400 gig Ethernet clients. If we move down below that, we have access networks, that's lower rates, shorter distances. We can see opportunities to deploy 100 gig, 200 gig coherent pluggables in both cable MSO networks and 4G, 5G XHaul, front, mid, and backhaul for mobile access networks. For cable distributed access architectures and cross-haul XHaul networks, we see the need to support point-to-point links over shorter distances, the need to support extended temperature for exterior cabinet deployments, line interoperability, multi-vendor support, and low latency, particularly for XHaul Edge, are also key requirements. And then in metro regional networks, there will be various ways to deploy coherent pluggables with support for a range of line capacities, line rates from 100 to 400 gig, with a much wider range of feature sets and capabilities. Of course, in this area, we do expect to see a mix of embedded performance optimized and pluggable footprint optimized coherent solutions depending on the needs, particularly in scenarios where there are trade-offs for pluggables where network functions such as CDC, for example, might not be supported. So then we just shift over, and here we look at the same three categories outlined in the chart before, but consider the specific focus and optimization for coherent pluggable feature sets in each of these application segments. One of the primary ways to group this is looking at whether either packet or OTN transport or both needs to be supported. So we start again at the top left with our 400ZR, and that's a prime example of a pure packet application with a very specific focus on extended Ethernet switching via interoperable, high-density, low-power interfaces. And then in access applications, just below that, emphasis is again primarily packet-based coherent pluggable solutions where density is a requirement, but so also is operational robustness, so for hardening for exterior deployments. As with single-span DCI and reach and multi-span support is not primary objective, but the ability to, on the other hand, to support legacy 50 gigahertz line systems would be. And then over on the right-hand side of the big box is where things really start to diversify significantly. That's where pluggables are used as optical interfaces in metro and metro regional networks. Here they could be deployed in a wide range of different types of platforms, could be focused more towards OTN transport or packet applications, or need to support both. These pluggables could be working a lot harder in certain cases with respect to having greater feature sets, such that might be more than just a line interface, optical interface, but a complete mux ponder system and a plug, for example. So this means the feature sets in these plugs need to consider support potentially for things like a range of different OTN overheads, GCC, for example, precision timing protocol, distribution of the network clock synchronization, support for colored versus colorless applications, different types of client signals. Maybe they need to support a regen functionality. The ability to work in a multi-span metro ROADM environment, much more complex, and that carries its own set of transmit and receive optical specifications. Supporting the functions for demarcating a service. And finally, leveraging the type of telemetry available in high performance, very high baud modems and bringing some of these into plugs. And again, as it's been commented earlier in this presentation by the other panelists, this is kind of an area where we expect a range of different types of solutions to support the needs of the new network build-outs, really depending on all of the different factors in the deployment. And we see that certainly in the last year, there's been a very big and very rapid adoption in the high baud 800 gig solutions not just in the very, very long haul submarine, but also as shown in the green there in terrestrial applications as well. And I hand over to Tom. I'll let you advance it to the next chart, Tom.
Thanks, Patricia. So we talked about the standardization and people have been looking forward to these modules for a few years now, and the industry spent a lot of time and effort on the standardization, and modules have been available for some time now. We've been going through validating the use cases, validating all of the interop, and I just wanted to highlight a few different trials that we've done, kind of showing operation. We worked with Telia to demonstrate operation and performance over open line systems. Did a really exciting trial with Windstream on a live network where we were able to do over 1,000 kilometers at 400 gig on again a third-party line system. And I think that kind of speaks to the level of performance is really quite good, right? There is a trade-off for power, but we're still able to achieve with this technology a really impressive level of performance. And then in the DCI application, this announcement that ADVA had done where they demonstrated interoperability over their line system, and really in the use case that 400ZR was designed for in a point-to-point. And there's been lots of validation of interoperability between vendors, and really I think this model that we've all been working toward is going to be really successful. So with that, I will hand it over to Kyle.
All right, great, thanks, Tom. So kind of going back to what Patricia was talking about in terms of all the different requirements and characteristics that go into where these different interfaces are deployed in the network. My buckets are slightly different than hers. I'm starting with Metro DCI and not really addressing the access too much, and then including the high performance long haul subsea core appropriate optics. So to really simplify this again, on one side of the spectrum, it really is all about profile or density or form factor. It's about pluggability, interoperability, integration into devices like routers and low cost. At the other end, it really is all about performance. We're really much less concerned with power and space. It's all about maximizing reach at rate or rate at reach and minimizing that cost per bit per kilometer because the distances are long. And then that real battleground where it gets interesting is where we have that balance of both, right? This is metro regional aggregation. And once again, this could be WDM system based or router based. So in terms of real world applications, this is a very high level summary of an OFC paper that you can go potentially look at in a couple weeks at OFC. And what we did is we looked at 3 different categories of optics. So kind of a ZR plus optimized for DCI and access in small metros. This 400 gig CFP2 multi-haul kind of optic that has a lot more capability. And then a 400 gig any distance high performance optic. And we modeled those homogeneous networks of those across metro aggregation, a metro regional core type network, and a long haul, ultra long haul backbone. And basically to summarize the table that I'll present in a minute is for each type of optic and each type of application, you ask yourself a couple questions. Can the optic run at 400 gig? Can it pass through ROADMs? And can it be put in a router? It's just kind of some basic metrics that allow you to evaluate the appropriateness of that optic in that application. So if we start at the top here, I'll be really quick. With ZR plus, the obvious sweet spot is in that metro aggregation where we can run links at 400 gig. With ZR plus, maybe we can pass through a ROADM or 2 for a small metro aggregation. I think that'd be okay. And generally, we can put them in the router and all the cost savings and space savings that flow from that. But as we get into metro regional core, a lot of the links won't be able to operate at 400 gig. We're going to have to dial that back to get better performance. Once again, we're limited in how many ROADMs we can pass through. And when you get to long haul, ultra long haul backbone, obviously these type of optics just aren't appropriate. Now, when we get into 400 gig multi-haul CFP2 type optics, the sweet spot really becomes that metro regional core because we can run almost all links still at 400 gig. We can pass through ROADMs, and we have that option of transponder-based or router-hosted. You start to run into some problems in the long haul where you have to, once again, dial back the links. And then over in the metro aggregation, certainly they still work, but is it necessarily the most cost-optimized, space-optimized way you could do it when you have the option of QSFP-DD? And then I think you know where this is going. The 400 gig embedded any distance type of optics, this is where the long haul, ultra long haul ends up shining, where we can still run links at 400 gig or potentially higher across any type of distance, whether it's long haul, ultra long haul, subsea. We can go through as many ROADMs as we need to, but of course we're now in the realm at this point where it's strictly an embedded transponder type solution. And so I think this just gives a little bit of a snapshot of where these type of optics are appropriate in various architectures. All right, Tim, you want to introduce the last section? I guess we'll go right to Tom. Go ahead, Tom.
Yeah, sorry. Tom, I'll turn it over to you for Acacia's point of view.
Sure. So just highlighting, our implementation of this technology. Acacia's been a big proponent of silicon photonics and has been using silicon photonics for a number of years. And in this generation, what we really did is kind of took the next step forward in terms of packaging innovation to combine our DSP, our silicon photonic PIC, our driver, and TIA into a single device. We call this 3D siliconization. This is manufactured in a high volume electronics manufacturing facility. And so it really eliminates the traditional optical packaging challenges and costs. And so we use this across all of these different products. It not only makes it scalable and better manufacturing, but reducing the number of interconnections has benefits for reliability. And really importantly, as we're pushing up to higher and higher baud rate, the signal integrity improvement by having all these devices co-packaged is really important because the limitation in performance is getting to where it's no longer coming from the devices themselves, but actually the interconnections between the devices. So, again, building on a common kind of engine for all of these different types of solutions, we think is a way to drive scalability while also being able to address a range of different market applications. And with that, I'll turn it over to Patricia.
Okay, thanks, Tom. So this slide will have an overview of Sienna's very broad portfolio, but highlighting in the middle our coherent pluggable offering and how that ties in. So our pluggable solutions are built on a very compact, very small, highly optimized, footprint optimized multi-chip module construct, what we call our transceiver on chip, where we're moving into the, let's call it the more than more era in component design. So we're stripping everything back to the dies. We're leveraging very advanced chip packaging techniques with multiple die elements to get the smallest possible footprint. That said, this TOC construct is very flexible, and we can program the individual DSP and electro-optic constituents of the TOC for specific applications and client streams. And so this allows us to support a very broad range of 100 gig to 400 gig coherent pluggable solutions. And that includes both standards-based interoperable as well as high-performance proprietary modes, the latter leveraging things like advanced forward error correction and probabilistic constellation shaping. So our pluggable coherent modems also leverage Sienna's fast NPI cycling, our supply chain versatility, and of course our vertical integration strengths, and all pillars that support the rest of our portfolio as well. And this extends to fully flexible instrumented photonic line systems, our WaveLogic coherent modems, which of course is both the embedded, very high performance modules, as well as the faceplate pluggable modules we've been talking about. It includes a range of packet optical platforms supporting high density modular interconnect, converged layer 0 to layer 3, DCI compact modular, and an extended family of switch routers. And all of these platforms supporting both integrated as well as coherent pluggable optics, and also tightly integrated with photonic layer solutions. And finally, this is rounded out by our software network design tools, supporting network design and planning, operational functions like link engineering, multi-domain, multi-layer, multi-domain control, SDN applications, and our emulation cloud suite. And I pass it over to Kyle.
All right, thanks, Patricia. So from the Nokia perspective, as a leading vendor of both routing and optical transport, it's really about optimizing the application based on who you are, based on the network operator or the service provider. And what we've seen is that we have operators who have a somewhat router-focused transport, where it's an all-IP network. They prefer simple optical transport, and they certainly are looking forward to these standardized router-based DCOs. And then, of course, there's more optical-focused operators where we might have packet OTN grooming, very sophisticated CDCF line systems, optical muxponders and transponders. And, of course, both of these can actually exist within one network operator as well. And, based on the application, we're going to see these type of approaches adopted, maybe router focused in metro, more optical focused in long haul. Different types of operators, competitive versus incumbent, will adopt new technologies at different rates. And even geographically, we see maybe a little more IP centrism in North America, a little more OTN optical focused in the rest of the world. And then, of course, there's near term versus long term. This is not going to happen overnight. These are very exciting technologies, but the operational inertia is pretty significant. But at Nokia, we're addressing both ends of this spectrum, whether it be our 7750 SR routers, which are designed really from the ground up with actually a very high capability to cool QSFP-DD ports, so that we'll have very, very minimal, if no restrictions, in terms of the type of pluggables that we can put into a QSFP-DD port within our routers. And then over on the right, the Nokia 1830 PSS, which of course has a complete line of different transponders and POTN grooming functionality. And then our Wave Fabric Elements portfolio is really that vertical integration of DSP and silicon photonics that once again we can put those together into multiple different optics in different form factors with different performance aspects that, of course, can then plug into either our 7750 SR routers and other routers, as well as our optical transport platforms. I'll turn it over to Tim for the conclusions.
Thanks, Kyle. Yeah, let's move into the conclusions so we can save a little time for Q&A. So just looking at kind of the evolution of coherent modems over time, from 17 through 25. In 2020, it was almost an even mix between embedded and pluggables. The vast majority of pluggables are used in China in their CSP networks, both metro and core networks. As I said earlier, we're expected embedded modems to continue to grow at about 10% CAGR, but the pluggables are going to be growing at about a 32% CAGR. This is unit volume growth, not revenue. And over the next 5 years, we're expecting that pluggables will be about 68% of the unit volume relative to all coherents. And, the pluggables are going to be in QSFP, DD, OSFP type packages, as well as CFP2 type packages. And as I've said, embedded modems will dominate long haul and subsea. We expect the point-to-point applications to be with the high-density form factor pluggables, and then the battleground for the metro regional between the CFP-type pluggables, multi-haul, as Kyle had said, and the embedded solutions. So looking out the optical network to 2021 and beyond, there's a lot of tailwinds. We've had with COVID, the professionalization of at home, the cloud service adoption, the digital transformation, working with collaborative tools, and then 5G support and edge compute. So there's a lot of tailwinds. We think this is going to drive the market up over this period of time. In 2020, we were just over 16 billion. We're expecting that to be a little bit over 20 billion by 2026. And as you can see here, about half of that growth is from pluggables. So we're not seeing, pluggables are not coming in and totally transforming this market. We see them as kind of an additive thing, adding about half the growth to the optical networking between 2021 and 2025. But there are still some tailwinds, and there's a lot of things with the vaccine rollout that is going to have uneven recovery. So there's going to be some turbulence, but in general, we're predicting good growth in optical networking. So I think I'll turn it over to you for a couple minutes here, Alan, and then we'll move into the Q&A session.
All right. Thank you, Tim. And thanks to our panel. Great discussion today. And we're going to go into the Q&A at this point. So if you have not done so already, please submit your questions via that Q&A widget that is on the left side of your screen. And also don't forget to check out the resource list widget. That's where you find all the resources from our sponsors, as well as that additional companion report written by Tim Monks himself. So, all right, Tim, let's go back to you and let's get into our Q&A.
Okay, Patricia, I'm going to give this first one to you. Others can chime in if they want. But the question is, can pluggable coherent modems be remotely software configured to assign wavelengths and line rates?
Thanks, Tim. Yeah, so software configuration is supported via the host interface to the plug. In general, that means the support for software configurable laser retuning. Depending on the type of plug, line rate reprogramming would be supported. Of course, the plug itself must support multi-rate features in this case.
Okay, thank you, Patricia. Anyone else, or we can move on? Tom, I'll direct this one to you. Can OTN functions be supported in coherent QSFP DD pluggables?
So there are there are some limitations today. In general, the QSFP-DD application usually goes into a router, so it's predominantly an Ethernet application. There are limitations in some of the I/O of the QSFP-DD, and most of the full OTN functional applications are typically using the CFP2 form factor. They're also generally less sensitive to the density. So I would say in general, most of the OTN applications will typically go toward the CFP2 form factor. Although you could use a DD with some OTN functionality behind to kind of pass in a sort of a pass-through mode, but that's a lesser use case for the DD.
Okay, thank you, Tom. Here's Kyle. I'll direct this one to you. For coherent pluggable modem deployments, does it affect the performance of the EDFA, erbium double fiber amplifier, for longer submarine transmissions, or how do they complement each other?
Let's think about that one. I mean, EDFA is certainly even part of the ZR spec in the sense that they spec out to 120 kilometers with EDFAs. The issue with amplified networks is that it becomes an OSNR issue, right? And these pluggables have some limitations in terms of their optical filtering, in terms of their OSNR. And so heavily amplified networks, like you might see in kind of a mesh kind of metro network, are going to be challenging for some of the lower performing pluggables. You're muted, Tim.
Tom, let me direct this one to you. How do you overcome the environmental challenges in general temperature and humidity when using pluggable optics in a field encasement?
Yeah, I think there are a number of ways to address it. I don't think that's something unique to coherent. I think the same techniques that have been used earlier, as the power is coming down, it becomes more manageable in those types of interfaces. We've demonstrated extended temperature capability on some of our pluggable products. I think it's a very solvable engineering challenge. I think it really is the challenge in access networks and for some of those industrial temperature applications has I think really been one of just defining the exact requirements and then designing to the requirements. But I don't think coherent faces any real unique challenge there that precludes it from those applications.
Okay, thanks, Tom. And this one I'm going to direct to Patricia, but others can jump in as well. So OpenZR Plus are optimized for regional DCI applications based on point-to-point amplified DWDM systems. Due to limited launch power, they have modest application for running across ROADM-based networks. Open ROADM use CFP2 form factors. Do you foresee a need for ROADM-friendly coherent pluggables in QSFP-DD form factor? And if yes, what do you foresee to be the general availability timeframe for such pluggables? There was a lot.
So that's coming to me first. That's a mouthful. That's coming to me first, Tim. I think so. The Open ROADM spec has specific transmit and receive optical specifications that would allow for the support of those ROADM network configurations. Some fairly challenging things like colorless drop and so on that would impact the type of optical receiver you have and so forth. So really there's a lot more scope and flexibility to do things like that in a CFP2 DCO form factor. So that would really be the form factor of choice. I don't think it completely precludes doing it in a DD, but certainly there's more latitude and leeway to cover those types of functions in a CFP2 DCO.
Yeah, I'll comment on that. I think there is a tremendous demand and application for a ROADM-compatible optic in the QSFP-DD form factor. We're just not there yet in terms of the technology. But in building, you want to optimize the topology of a router network, and that's very often going to mean passing through ROADMs. And we don't want to have to limit IP over DWDM networks to very, very simple kind of point-to-point topologies. So I think as the next generation of DSPs get lower power and more highly integrated, we will likely see that a generation from now.
Yeah, I guess if I can add, I agree with that. I kind of look at it as a toolbox, approach where the tools in the toolbox today support you can do that functionality in a CFP2. You can do other types of architectures in the QSFP-DD, and there's workarounds, but over time, I wouldn't bet against that not being available in a DD. I think we've seen the industry over the past 20 years has always been able to innovate and address solutions like that.
So we're at the top of the hour. We haven't got to all the questions. Sorry about that, but we will be following up with you directly via email on questions that weren't answered. So thank you, everyone, for attending the webinar. I hope you found this informative and helpful, and have a good rest of your day. Alan, turning it back over to you.
Yes, thank you, Tim, and thanks for leading our discussion today. We do appreciate that. And a special thank you to all of our presenters, from Tom and Patricia and Kyle, for this very informative and engaging discussion today. And I do want to thank our audience as well for submitting all of your questions and comments. As Tim mentioned, we received a ton of questions, so our panel will be following up with you afterward to kind of address those questions going forward. So an archived version of this webinar will be made available shortly. In fact, we'll be sending you a follow-up link on how you can access that archive, or simply use the same link that we sent you earlier. Come back, view this session again, pass it along to your colleagues if you so choose. A survey is going to pop up at the conclusion of our webinar, so please take a few moments to complete that, and continue to follow us on Twitter and LinkedIn for information on future webinars from Omdia, brought to you by Informatech. So again, thank you for joining us, and have a great rest of your day.